Thank you very much for inviting me to speak. And so this talk this project is recent. It started around 1 year ago, and we did it with my collaborators, Barbara Beatty, Bella Finkel, Bernd Strumpfels, and Bella Zakovic. Okay, so let me start with the basic story, basic setup, and probably for most of you, these slides will be slightly boring, but I really want to make a self-contained talk. So the main variety for me today will be the moduli space of n distinct points on a projective line, modular PGL2 action. So these are given by this Möbius transformation of projective line. And this M0n can be thought by you as the various quotients. So for instance, open Grassmannian modular torus action, where we act with the torus on each column of 2 times n matrix. Or you can think about projective lines, product of projective lines without diagonal modular PGL2 action. And for me, a point from M0n today will be given by a matrix, 2 times n matrix. So I can act with the torus and make all the ones in the first row. But also, of course, I can act with a GL2 or PGL2 group and put 3 points on a P1 to some fixed 3 points. Since PGL2 action on a projective line is 3 transitive, I can always do this. So usual choice is 0, 1, and infinity, which you can see in the first, second, and the last column of the matrix. And this choice is usually called gauge fixing. And today, I want really not to do this in most cases. So for me, gauge fixing will be something not very good, because you can see that I break symmetry, nice symmetry of M0n that preserves this endpoint. Okay, so in particle physics, we are interested in computing scatter and amplitudes, and this is a certain functions. So let's say I have elementary particles, n of them, so I can fix momenta in a space-time. So these are vectors P1 up to Pn, and my amplitude will be a function of this momenta. And how I like to think about amplitudes, that it gives me a probability density of a certain scattering process with given momentum. And as you all know, that there is this expansion of the amplitudes, that this can be actually seen as a sum over amplitudes given by loops, where each A and L is a sum of certain integrals, which we can read from a loop Feynman diagram. So for me today, everything will be relevant only on the 3-level amplitude. So when I have 0 loops, and yeah, more explicitly, I'm also talking about bi-joint scalar phi3 amplitudes. So what is important is that if I want my amplitude to be non-vanishing, I want the following be satisfied. I want the sum of momenta be 0. And also, since space-time is invariant under Lorentz group, then we can actually say that amplitude should be a rational function in certain Mandelstam invariants, which are encoded in this momenta vectors. So Sij, also was mentioned by Helena, are just pi plus pj squared. And then momentum conservation translates to a linear system. So we have n linear equations in these Sij variables. And you can also read from properties of momenta that Sii are 0 and these Mandelstam invariants are symmetric. So what will be important for me is the formula for the 3 amplitude, which was given by Kachar, and Yuan in 2014. And for this, I need to define a scattering potential. And scattering potential will be this function, L of x, which is just, in fact, it's a log likelihood function well defined on M0n. So due to momentum conservation, due to this linear equations, this function is actually PGL2 invariant. So you can shuffle your points with a PGL2 and this function will not change. And what they did, they said that the correct way to compute this tree amplitude would be compute critical points of the scattering potential. So I'm taking partial derivatives, and I obtain such rational function equations with parameters given by Mandelstam invariance Sij, and these are indeed Plucker coordinates of my fixed matrix in the denominators. And for generic Mandelstam invariance, so for generic kinematic data, there are exactly n-3 factorial solutions in M0n. So from mathematical point of view, we use this procedure, and for us it was just maximum likelihood estimation. So whenever I want to understand how my parameters are actually close to actual density, probability density, we usually do maximum likelihood estimation. So we take this log likelihood function, which is exactly the scattering potential, and we optimize, so we look when it takes its critical values, which is exactly done by taking the partial derivatives and solving the corresponding rational function system. And there is a nice theorem by Juniha, which states that the number of critical points of these critical equations are actually encoded in the geometry of the underlying variety, which is M0n for us. And this is a topological Euler characteristic of M0n. And you can check that this is indeed n-3 factorial. So if you were also present at Claudia's talk on Monday, we did this many times by exclusion-inclusion formula, because Euler characteristic is also additive. And as Bernd sometimes says, that what we are doing in nonlinear algebra community is that we take whatever problem we can find and add degree to this. So maximum likelihood estimation problem leads ML degree of a certain model. So we have that this number of critical points, I will call it ML degree of M0n. Okay, and the way to read scattering amplitude is as following. So I need to compute Jacobian of my system, which is also the same as Hessian matrix of my log likelihood function. This will be given by second partial derivatives. And to compute my amplitude, I need to evaluate localized integral on M0n at the critical points that I just computed. And this is happened to be the sum of certain residue functions over the solutions of the critical equations. So here you can, who is familiar with this, you can also recognize Parker-Taylor factor, which is this 1 over Plucker variables of my matrix. Okay, so now I'm coming to the setup of my talk. So now we're interested in the following question. The question is, what happens if we set some Mandelstam parameters to 0? And since they are labeled by pairs of indices, ij, it is convenient to do this with respect to some graph. So because the edges of the graph are exactly all possible pairs of indices, and I can create a rule for which I select Mandelstam invariance to 0 with respect to some graph. And then the question is, of course, for each graphs, we still have something well-behaved. And here, what is important that gauge fixing is not always good, because basically gauge fixing saying that your first Mandelstam invariant S12 with this choice will never appear in scattering potential, so you always assuming that it's non-zero, so you can't set it to 0. And the same is for any Mandelstam invariant which is something n, because my last point is selected to be infinity, so I will never see Sin in my scattering potential. So we don't really want to do this gauge fixing. And then we are considering the matrices on the left. And the matrices on the left are not encoding only one point from M0n, but they encoding the whole orbit of PGL2 orbit of points in M0n. So you can think about this as a variety which is isomorphic to PGL2, and this will be some surface in a Pn-1 space. Okay, now I want to briefly talk about motivation, how this idea actually came up. And the motivation came from also a recent paper from 2024 by Nick Early, Annel Twist, and Ben Strumpfels, who considered minimal kinematics given by two trees on M0n. So they did exactly the same. They took usual scattering equations, and then they asked a question: what if we set some Mandelstam invariance to 0, but they wanted to obtain only one critical solution to the critical equations in this case. So they called it minimal kinematics, and minimal kinematics corresponds to ML degree 1. And why this is meaningful? So from algebraic statistics point of view, this is meaningful because when you do maximal likelihood estimation, you actually looking for only one critical point, which is an actual estimate, maximum likelihood estimate. So if you have ML degree 1, then you find this point immediately. Also, what is nice in this case, whenever you have ML degree 1, then this solution, so critical solution to scattering equations, is actually a rational function in Mandelstam invariance. And there is a nice procedure to obtain the form of this solution called Horn-Kapranov uniformization. And you can actually write down this rational function in Mandelstam invariance. And it's also known that in the numerator and denominator of this function, you will see only product of linear factors. So this gives you a really nice setup. And they proved in particular that these choices of minimal kinematics are in bijection with two trees on n-1 vertices. So 2 tree is just a very special graph. So when you're in the setting of this very special graph and you set up Mandelstam invariance to 0 that are non-edges of this 2 tree, then you actually number of critical points drops from n-3 factorial to 1. But this is also done with a gauge fixing. So in particular, when we started looking at various graphs, we found minimal kinematics that are not coming from 2 tree because we don't do this gauge fixing. Okay, what does it mean for the amplitude then? So of course, to each graph, we can associate an amplitude. And this is done just by putting Mandelstam invariance to 0, because amplitude from CHY procedure is exactly a rational function in Mandelstam invariance. And whenever your graph is planar, then you can think about this as this amplitude is a degeneration of bi-joint scala phi3 amplitudes that we started with. And for instance, this is always the case when your graph is a 2 tree, which is also a triangulation of n-gon. But when it's not, then it's interesting to ask what can we do beyond planar case. And probably also, as most of you know, that there was a work by Arkani Hamed from 2015, which introduced on shell diagrams. So these are also some special diagrams that give us amplitude beyond planar case. And it's very curious that in algebraic geometry, these on-shell diagrams are in bijection with another set of graphs, which are called hypertrees, and were introduced by Kastrova and Tevelev in 2013. And what is also curious, there is a link to our variety M0n as well, because these hypertrees define irreducible effective divisors. So the question we want to ask, maybe we will not focus too much on hypertrees themselves, but the question is, what can we say in general about any graph? So what happens to ML degree? What happens to critical points to the scattering equations? That's the question we ask. I think that yeah, exactly. I think it's yeah, I think this is a consequence of the fact that we always use momentum conservation, so it makes our functions PGL2 invariant, so you can always switch pole to the numerator. Okay, yes. So I don't want to focus on hypertrees. Perhaps they have more physics relation, but I want to really talk about general setting right now. So I fix a simple graph on n vertices. So I abuse notation slightly, and G for me is graph itself, but also the set of edges of G. And I set Mandelstam invariance to 0 exactly when Ij is a non-edge of G. So what happens is our kinematic space changes as following. So it's still, kinematic space is a solution set of a linear system, but now my linear equations are given by some of those Mandelstam invariants that are still alive. And of course, as for every linear space, we want to know what is the dimension, or equivalently, what is the codimension of this linear space. And we can answer this question, and it has some nice combinatorial interpretation, which I will come back a little bit later. And also, when we are interested in scattering equations or solutions to scattering equations, it makes a total sense to define this incidence variety. So for this, I will take pair of kinematic data and solution to scattering equations, so S and X, where S is from kinematic space and X. So I will switch sometimes, as I will think about X as my matrix with one rows. On the first row, coming from M0n, or I can also think about n coordinates. So naturally, I can also put them into P n minus 1, but without certain Brett arrangement given by union of the hyperplanes xi equals to xj. So I don't really want these coordinates to collapse with each other, such that my critical equations are satisfied. So these are just definition of the critical equations. And this incidence variety comes with two natural projections. One is to the left to the kinematic space, and another one is to Pn minus 1 without this Brett arrangement. Or I can also, by bypassing to a nice open set, I can also sometimes say that I'm actually projecting to M0n. So exactly, so this is because I don't gauge fix. So when I speak about X point in Pn minus 1, what I mean is actually that every solution to my scattering equation is not a point, but it's a whole hypersurface, it's a whole surface which is isomorphic to PGL2 orbit. And when I project to M0n, what I'm doing, I'm actually selecting some representative of PGL2 orbit to obtain a point on M0n. And we want these projections and these incidence varieties to be nice. And what it means that probably for general kinematic data, I really want to see finitely many critical solutions of my scattering equations. So I want this map to the left be finite to 1. And also probably I want to be able to reach every general point from M0n as a solution to my scattering equation. So this means that my map to the right should be dominant. Okay, here comes two first examples. So let me consider complete graphs first. And when I talk about complete graphs, it's actually a basic setup of scattering equations. So I don't fix any Mandelstam invariance to be 0. And as probably you know that for n equals 4, I have ML degree 1. So I have 1 critical point. And whenever I set some Mandelstam invariance to 0, my ML degree can only drop. So in the case when I have 1 critical point, if I don't gauge fix, then equations defining my scattering correspondence, this incidence variety, is equivalent to the following 5 equations. So the first row is modified momentum conservation, and the second row is actually giving me this surface isomorphic to PGL2 orbit. So this surface means that once I fix 3 points via PGL2 action, then you will see a unique solution to the scattering equation. And if I set any Mandelstam invariant to 0, then ML degree will drop, so I will have 0 solutions. There is not much choice. So it's a little bit more interesting for n equals 5, because for n equals 5, usual scattering equations have ML degree 2, so 2 critical points. And then we have various cases. So whenever I set only 1, so everything is up to relabeling. So I can set any edge to be, I can remove any edge. So I set S for 5 to be 0, and ML degree drops to 1. Or the same happens when I set 2 non-adjacent edges to 0. But if I set either adjacent edges to 0 or more than 2 edges to 0, then actually the system becomes inconsistent, and I will have no solutions to critical equations. Okay, so as you can see, some graphs are nice and some are not. And so some give me solutions, critical points, and some don't. And for n equals 5, we saw that only 3 graphs up to isomorphism are fine, and we will call them copious. And our main result is basically characterizing these copious graphs from different perspectives. So we have 4 notions of copiousness, and we say that the graph can be either geometrically copious or matroidally copious or algebraically copious. And these are actually equivalent notions, and they all are also equivalent to topological copiousness for graphs with a universal vertex. And the other implication holds for every possible graph. So how can you think now about this notion? So first of all, we can define ML degree very similar way as we did for usual scattering equations. And this will be just some invariant associated to a graph, mu of g, which counts the number of complex solutions to modified scattering equations, to graphical scattering equations. But what is important, I only care about solutions in M0n. So I still want all the coordinates, all the points to be distinct. So for example, this invariant of complete graph is exactly ML degree of M0n. And for instance, we will see that whenever this graph is copious in any of these notions, then every vertex should have degree at least 3. So you can think about copiousness as the fact that the graph has enough edges for these scattering equations to be well defined. Okay, before I come to definition of this copiousness, I want really to talk about momentum conservation a little bit more. And the thing is that, of course, for every choice of the graph, I select certain Mandelstam invariants to be 0. But it might be that momentum conservation, which is a linear system, forces more Mandelstam invariants, which are not non-edges of my graph, to be 0 as well. So I don't really want this to happen. And that's why, so in this meaning, I want to select graphs which are maximal for fixed scattering, graphical scattering potential. So I'm saying that graph G is compatible with momentum conservation if the solutions of the momentum conservation, so kinematic space vectors intersected with the torus, are not zero. So I can find solution of momentum conservation with all non-zero coordinates. And it turns out that this has a nice combinatorial interpretation. So this happens when the so-called even cycle matroid of kinematic space has no co-loop. So here we want to study matroid, which is obtained from a linear system given by momentum conservation. So if you don't know what is a matroid, you can really think about, in this case, vectors in a vector space, and you want to understand what are all possible linear dependencies among these vectors. And it turns out that momentum conservation is a known matroid in combinatorial literature. And this is what is called even cycle matroid. So it's given for any graph. And we can describe any matroid by giving a list of its circuits. So these are minimal set of vectors that are linearly dependent. And the circuits will be given by the following objects in the graph. So these are circuits of the even cycle matroid. And the claim is that this is enough to define a matroid completely. And this consists of even cycles of the graph. So cycles of even lengths, for example, but also odd cycles joined by a vertex. Or for example, like this. Or also odd cycles joined by a path. Or for example, like this. So these matroids were studied a lot by Zaslavsky, and basically from his research, we can figure out that equivalently, I can say that G is compatible with momentum conservation when it has no degree 1 vertices, but also no edge that belongs to every odd cycle, or equivalently, no such edge that whenever you withdraw this edge, you don't really want to see a bipartite graph. So this is equivalent. And as a corollary, we can read that codimension of kinematic space is the rank of this matroid. And from the Zaslavsky works, it's also clear that the rank of this even cycle matroid is n minus number of bipartite connected components of the graph G. So for example, for complete graph, since it is connected and also non-bipartite, we have nothing to subtract. So as this codimension is n, as you can also understand from usual CHY scattering equations. And for this graph, without these 6 edges, it's actually a bipartite graph K33. And then this codimension will be n minus 1. Okay, now I want to come back to this copiousness. So these notions that characterize graphs that will be nice for me and that I want to consider. And I will start with this geometric copiousness. And for me, the graph will be geometrically copious if these projections that I already mentioned, that they are nice. So first projection to M0n, I want it to be dominant, so surjective on dense open set. And projection to the kinematic space, I want to be finite to 1. And then I can actually define this ML degree because it's well defined. So mu of G will be degree of the second map and the number of critical points for the graphical scattering potential, which is obtained by specialization of usual CHY scattering potential. And also this is a number of points in the general fiber of this map. Okay, so for some intuition, I want to lead you through this lemma. So whenever we have geometrically copious graph, then actually the degree of each vertex should be at least 3. And this is exactly why. So assume that a vertex is of degree less or equal than 2. Then if the vertex is of degree exactly 2, then I can connect. So I have 2 edges incident to vertex I, let's say ij and il, and which means that one equation in the momentum conservation will be exactly Sij equals to minus Sil, so it will be a binomial. And if you then substitute this relation to scattering equations, you will see that scattering equations force xj to be equal to xl. But we agreed that we want a point on M0n, so all n points should be distinct. So this cannot happen on M0n. So you don't get dominance to M0n. And if you have a vertex of degree 1, so it means that the set of edges incident to vertex I consists of one element, and you will just observe that one variable among your n variables just doesn't occur at all, and this will mean that the fibers are either empty or positive dimensional, which we also don't want to have. Okay, so now since we are talking about graphs, I really want to characterize this copiousness in terms of combinatorics somehow. And this is how this another matroid comes to the room. So we will call it scattering matroid. And scattering matroid can be also seen as a representative matroid given by a certain linear system. So what is a linear system? Basically, this is a system defining my incidence variety. So I take all my equations together. So first I had momentum conservation equations. This gives me n equations, and this is, of course, linear system, linear over integer numbers. And also I have scattering equations, which are my rational function equations. But once I fix some point on M0n, so once I fix my axis, this also becomes linear in Mandelstam invariance. So I can say that these n scattering equations are linear over rational function field in x variables. And we can say something about the scattering matroid. So for instance, we know that the rank is bounded, and this is not full rank, so it's bounded by 2n minus 3. And equality happens to be for complete graph, exactly. Yeah, but so if you fix general x, and this matroid will have the same combinatorial properties. So I can actually fix some general x, and it will not. It can be some bad x, yeah, but if you fix x from some open subset of M0n, it will be fine. Exactly. So by the matroid, I always mean, so in my talk, I will only have representative matroids. So you can think about matroid as a matrix, which I, by the way, will show in the next slide. And you can think about elements of the matroid as the columns of this matrix. And then bases are maximally independent, linearly independent subsets of these columns. Circuits, for instance, are minimal dependent subsets of these columns, and so on. Okay, so here comes this probably the most complicated definition of copiousness. And a graph G is matroidally copious if the following is true. So first of all, the rank of this matroid, I want it to be the rank of this matroid without any column. So basically, this condition means that I don't want to see call loops of my matroid. And call loop is an element which is present in every basis. And also, I want this rank to be expected rank. So as I will show you in the next slide, the way I constructed this matroid, I took momentum conservation equations, and I also took scattering equations. So the metrics are just coefficient metrics of all my equations. So on top, you will see the metrics of this even cycle matroids that we considered for momentum conservation. And on the bottom, I will see metrics for scattering equations. And the rank of momentum conservation matroid is this kappa G, which we just found on previous slides. And the rank of the scattering equations is n-3 because it's the dimension of M0n. So I really expect the rank of this big matrix where I stacked two matroids together to be kappa of G plus n-3. And then I also want this slightly probabilistic condition. So exactly whenever I fix my general point from M0n, or you can also think about general point in Pn-1 without this hyperplane Brett arrangement, I want the sum of the kernels of these matrices for fixed general points span the whole kinematic space. So for every point from M0n, this kernel gives me actually the fiber that I see on top of this point of M0n. And I want these fibers together cover the whole kinematic space. And equivalently, you can think about dimension conditions. So equivalently, instead of taking the sum, you can take intersection of row spans of these matrices, and the dimension should be the correct dimension. So this should be co-dimension of the kinematic space. So let me show you this matroid. So this is an example for the complete graph K6. So for K6, we have 12 Mandelstam. We have 15 Mandelstam invariants. And we also have 12 rows because first 6 rows are exactly coefficient matrix of momentum conservation. So these are sum of Sij should be 0 for each I from 1 to 6. And the next 6 columns, you can see that this is actually a matrix which is defined over rational function field in X variables. So my claim is exactly whenever I fix a generic point x1 up to x6, then all these matrices will have the same rank, the same basis, and so on. So the same combinatorial properties. So in particular, one consequence of this definition of matroidally copious graph is as following. So the rank of this matrix, so you can think about the rank of the scattering matroid as the rank of this matrix for general X. So I select general X and I can compute this rank. And this is given by this kappa of G plus n-3 from the definition of matroidal copiousness. And in particular, we can show that this number is always less than number of edges in G, which is one size of this matrix. And it's also always smaller than another size of the matrix, because another size of the matrix is 2n, and we also know that the rank of the scattering matroid is always bounded from the above by the rank of the scattering matroid for the complete graph, which has rank exactly to n-3. So this matrix is always not of the full rank, which means that with this notion of copiousness, we can always find some solutions, some non-trivial solutions to this system. And that's what we wanted. Okay. Almost the last notion. So I want to study commutative algebra of the incidence variety that I defined. So I had a set of pairs of points, kinematic data together with point from M0n. And for this, I really want to think about the vanishing ideal of this variety. So let Ig be the scattering ideal. So this is the vanishing ideal that defines the closure of my incidence variety that I consider. So the closure of the incidence variety will be always a reducible variety, because basically you can think about this as a vector bundle. So you took some open dense subset of M0n, and the fiber above each point will be some subspace, some linear subspace of the kinematic space. So it's really a vector bundle. So when you take a closure of its total space, you will get something irreducible. And we are looking for a prime ideal, and there are 3 approximations that we can make. So we call it IG0, IG1, IG2. So what are these? So first, very naively, you can just take the definition of this incidence variety, and this was defined as a set of pairs which satisfy momentum conservation, but also my scattering equations. But my scattering equations were rational function equations, which I don't want to see in the ideal. So naively, I can just clear denominators. So these are my scattering equations with clear denominators, and these obviously vanish on my scattering correspondence. So in practice, what I will do to find my actual prime ideal of scattering correspondence, I will take momentum conservation and these scattering equations with clear denominators, and then I will saturate by all the denominators, by all the differences xi minus xj, because I don't want them to be 0. And at some point, my claim is that I should reach the prime ideal that I'm looking for. But the better approximation is as following. So it's not completely obvious, but what happens is actually that the following symmetric functions, they vanish on the points of my scattering correspondence. So they are also in the ideal, so I can just add them to ideal I already considered. And the next approximation is actually came from a general setup for hyperplane arrangement. So we can consider certain moduli of derivations, and these derivations are defined, so they define the Naser relations, which also vanish on my scattering correspondence. So here is slightly combinatorial definition. So I can take a subset of vertices in my graph, and I say that this subset T is a separator of G. Whenever, if I remove this subset, I will get more connected components that I had before. And I can consider, after removing this separator, I can take any connected component, which I get, and I consider the following sum. So I sum over all vertices from this connected component of the products of xi minus xt, where t is a vertex from separator set that I removed, times my critical equation. And so if you check it by hand, then everything is miraculously cancels, and this indeed vanishes whenever you have a solution to critical equations. And this is the best approximation that you can take. So you consider this ideal, and maybe you need to saturate a little bit less to find the correct prime ideal that we are looking for. Okay, the correct definition would be as following. So this IG can be realized as a sum of following ideals. So speaking geometrically, I want to consider a prime component of any of my approximations. So here on the slide, I'm taking the first approximation, but I can also take beta approximation. So I can substitute IG0 by IG1 or 2. It doesn't matter. And then I look for prime components of approximation, and I'm looking for a unique prime component which doesn't have any polynomials purely in x variables, and which intersects kinematic space in exactly momentum conservation. So in other words, I don't really want to see some pure condition in x variables, because this will mean that I'm actually trapping in some subvariety of M0n. And I also don't want to see some relations in S variables that are not coming from momentum conservation. And we call graph algebraically copious whenever this proper prime ideal defined on top of the slides is non-empty. So since my scattering correspondence was a subvariety of a product of two projective spaces, so the first one was a projectivization of my kinematic space, and another one was just Pn minus 1 because I have n coordinates. There is a natural multi-degree assigned to the variety. So geometrically speaking, I can fix hyperplanes, several hyperplanes in first projective space and several hyperplanes in another projective space. So such that their number sums to the dimension of my scattering correspondence. So I'm slicing with the same number of conditions that is the dimension of my variety. And I obtain a multi-degree list. So for different choices of hyperplanes from the first and the second vector space. And equivalently, you can think about this multi-degree, or in this case, bi-degree, as a big homogeneous form from a cohomology ring of product of projective spaces. And the result is that one special coefficient, so the first coefficient that we will see in this multi-degree, so when I select all my hyperplanes from one projective space only, is actually gives me this invariant, which is a multi-degree of the graph. So the number of critical points to the graphical scattering equations. Yeah, okay, here you will see on the example, yeah. So for example, for the complete graph, we can actually see what is the scattering ideal defined in scattering correspondence. And this is a complete intersection. It turns out to be a complete intersection. And for complete intersections, you can compute this multi-degree form easily by multiplying multi-degree forms for generators. And this is the coefficient n-2 factorial that we need. So this is obtained by selecting all the hyperplanes, so the maximum number of hyperplanes from the projective space where, let me see, where M0n lives, I think. And you can see that it turns out that this coefficient is n-2 factorial. So if you define n-2 factorial by n-2, you will get exactly n-3 factorial, which is a multi-degree of M0n. Okay, so returning back to some small graphs, so small example for n equals 5. As you might remember, we saw only 3 copious graphs up to relabeling. And this was a complete graph without one edge and complete graph without 2 non-adjacent edges. And you can see the multi-degree. And what is important, that whenever your graph is copious, you will actually see these extreme coefficients always. So they will be non-zero. And what can we say about scattering ideal? So for complete graph, we always have a complete intersection. And this complete intersection is always generated by momentum conservation and those symmetric polynomials that I showed you in second approximation. And for other two cases, this is not enough. So for any graph which is not complete, these symmetric polynomials are not enough. And you will also see in the prime ideal some extra stuff, some extra generators. So let me show you non-copious case. So what can go wrong? So let me consider a graph, which is an edge graph of triangular prism. So this is my graph for n equals 6. And this is not copious. In particular, if you remember the definition of geometrically copious graphs, then the map to M0n will be not dominant. And how can we see this from commutative algebra situation? So first observe that whenever you compute this multi-degree, you will not see tau to the 9. So the last term which appears is sigma 8 tau to the first power. So the last coefficient is 0, and this is a criterion for non-algebraically copiousness. And whenever you actually compute this prime ideal IG after saturation, you will see that it contains a cubic generator purely in x variables, which means that your point in x variables can be solution to the scattering equations only if it lies on this hypersurface inside M0n, which is, of course, not open-dense orbit. So projection to M0n is not dominant. Okay. So any questions here? Because one of the results that 3 definitions of copiousness that I mentioned, they're equivalent. And now I come to the last one. And for this, I need the notion of the very-affine variety. So my variety is called very-affine when it can be embedded to a closed subvariety of a torus. So equivalently, it's ring of rational function is generated by units. And this theorem by Juni-Hu we already saw that whenever we have a very affine variety, we can think about this as a statistical model, and we can consider maximum likelihood estimation on that, and ML degree is given by topological Euler characteristic. And in our setting, we will deal with a very affine variety MG, and our graphical scattering potential can be realized as a usual likelihood function as you're used to it, where now the arguments of the logarithms would be some generalized cross ratios. And by generalized cross ratios, I mean some product of usual cross ratios, so you can think about also homogeneous functions, rational functions in Pluka variables. So how to obtain this very affine variety? Since we have momentum conservation, this what makes our scattering equations actually PGL2 invariant, we can consider the lattice it generates. So I'm looking at the integer solutions of the momentum conservation, and this will be some free abelian lattice of certain rank. So I can select a basis of this lattice. So let's say I have a basis given by vectors u1 up to ur. And for each such vector, I can associate a generalized cross ratio. So I have an integer vector, but then I substitute each Mandelstam invariant by this Pluka variable xi minus xj. So I obtain some Laurent monomial in these differences. And these generalized cross ratios actually give me an embedding of my variety into the torus of dimension given by the rank of the lattice. And I say that my graph is topologically copious whenever this map given by generalized cross ratios is an embedding. So in particular, we can use Juni-Hu's theorem again, and for topologically copious graphs, the number of critical points to my graphical scattering equations will be given by the Euler characteristic of the image closure in the torus of this map. So I have another variety which contains M0n as an open-dense subset, and I would like to call this variety a partial compactification of M0n. So I assign some extra boundary strata to M0n. Here is an example. So I consider octahedron on 6 vertices. And this is exactly an example of the graph without universal vertex, so no gauge fixing is possible. If you solve momentum conservation equations over integer numbers, you can find some basis of the lattice. So for instance, first vector is E13 plus E24 minus E14 minus E23. So this is a generator of the lattice, and I can translate it to this Laurent monomial in differences. So I embed with these rational functions my M0n variety, and the image closure in the torus is actually a complete intersection given by these 3 polynomials in Z variables. So for those of you who are familiar with U equations, you can think about these Z equations as generalized U equations for this partial compactification. And my graphical scattering potential as a function on the image can be written in these z variables. So once you substitute z variables back to these generalized cross ratios, you can actually modify your graphical scattering potential back to the ones that we saw already. And the number of critical points will be Euler characteristic, which is 2 in this case. So let me maybe go faster a little bit. So every graph which admits a universal vertex, this is equivalently with saying that this graph admits a gauge fixing. And such graphs are always topologically copious. And this is because the very-affine variety corresponding to these graphs can actually be realized as a complement of a hyperplane arrangement in some affine space. And the embedding that I just showed will be always linear in this case. And in this case, we also create this theorem, and we call this theorem due to Varchenko and Zaslavsky because they contributed a lot into this field. So in this case, ML degree is also the number of bounded regions in the complement of this hyperplane arrangement, and this can be read from the combinatorics. So there is so-called characteristic polynomial of the hyperplane arrangement, which is in this case also coincides with the chromatic polynomial of the graph. Certain invariant associated to graphs, and you can just evaluate this polynomial at 1 to obtain our ML degree. And here is example for K6 without one edge. But in general, we conjecture the following formula. So we conjecture this type of exclusion-inclusion formula for any ML degree of any graph. And here you basically can think about that these s minus 3 factorials are Euler characteristics of smaller M0 Ks that we conjecture that they should appear as a boundary strata of this partial compactification. So in the case when you actually have no cycles, we can prove this formula by looking at this boundary strata as maps from boundary strata from Deligne-Mumford compactification. So for instance, for complete graph, ML degree is n minus 3 factorial, but whenever you have 2 edges in the complement of the graph, then each edge in the complement gives you a boundary stratum, which appears in this very-affine variety Fg, and which will be isomorphic to M0 n minus 1. And M0 n minus 1 has ML degree n minus 4 factorial, and so on. And whenever they intersect, you will obtain something isomorphic to M0 n minus 2. Okay. So curiously, that you can observe that this formula can be quite big. So it's like it can be a very big linear combination of these factorials, which exactly happens for one example of hypertrees, which are also, you can think about them as bipyramids. So you fix some cycle, and then you fix 2 vertices, and you connect these vertices to the vertices of the cycle. So this is one example of hypertrees. And we prove that, these hypertrees, the special hypertrees, they are topologically copious, and also that the ML degree, which is this long series of factorials, point-wise is the same as n minus 4. So for every n, this long series evaluates at n minus 4. And the conjecture, so since hypertrees are relevant to physics because they correspond to on-shell diagrams, it would be nice to have the results that they are copious, so that they define a meaningful graphical scattering equation. So we conjecture that all irreducible hypertrees are copious. I don't have any time. Yeah, okay. So yeah, here you can look again at the 15 copious graphs for n equals 6. And yeah, this is all the notions that, all the invariants that we can associate. Multi-degree, ML degree, but also we can compute discriminant and the degree of the discriminant.